these are our last main topic. We're going to look at. Although I may add in, we may look at other topics as well. This is our kind of last serious topic. Okay, so quadratic residues. So let P be an odd prime. That's a phrase number theorists like using, but it just means it's a prime bigger than 2. 2 is kind of special, it's an odd prime. So we're not too bothered about what happens modulo 2. Modulo 2, the world isn't that interesting. It's just 0 and 1. Not too much going on there. But so last time what did we do last time? Well, we started by investigating again the quadratic formula and the quadratic formula, which give the roots of a quadratic equation in terms of coefficients of the quadratic polynomial, and we attempted to replicate that for quadratic congruences, quadratic polynomials congruent to 0, modulo prime numbers, say. And we discovered that we needed the ability to talk about elements of the multiplicative groups ZP having square roots or not having square roots. And then we looked at some examples, which I'll do a little bit of a sage program this morning to summarize. But just to recall the definition, let's stick with that. So W is a quadratic residue. Just get the definitions again. A quadratic residue modulo P means there exists another congruence class U, so a U in ZP, such that U squared is congruent to W modulo P. If you like, so you kind of in the back of your mind, you're connecting it with what we already know about real numbers and their properties. U is the square root of W, or U is a square root of W. So we tend not to use the phraseology square root. We definitely tend not to use the square root symbol. So we avoid using the square root symbol to denote these things in number theory. So W is a quadratic residue if there exists something such that when you square it, you get W. W is what's left behind after dividing by P, after dividing a quadratic thing by P, dividing a square by P. And similarly, W is a quadratic non-residue. Modulo, it always has to be with the suffix modulo P. If there does not exist any U such that U squared is congruent to W modulo. So if there is a U such that U squared of W is called a quadratic residue. And if that's not the case, then we call it a quadratic non-residue. So last time we investigated a few examples. Okay, and I just want to show you how nice it is to use MATLAB just to quickly generate up those examples again. And we'll also use that to motivate the couple of results we're going to do this morning, our first kind of theorems about quadratic residues. Okay. To get that. Any questions about the definition itself? So up to this point, we hadn't discussed the notion of a square root in the system. And the examples before we looked at last week showed that some elements were quadratic residues and some weren't. And with the few examples we're going to look at now, we'll quickly begin to spot some definite patterns. That that will motivate the results. That will motivate the results we're about to prove. Okay, so I'll just switch over to the screen now. So I'll do this in Sage, but you can very easily do this in MATLAB as well. So we're going to test a load of prime moduli. Often takes a while for the tab completions to load. Let's get into it. So what I want is this primes. I believe you can give it it's an iterator, and I believe you can give it a start and an end. Prime start stop, and it gives you an iterator for all the primes between certain. We'll look at all the primes between 3 and 20, say. We'll define Z to be the integer mod ring modulo P. So this object Z is the integer mod ring modulo P, the ring of integers modulo P, which is as part of that is the multiplicative group modulo P. So I'll just start defining a few sets. So I'll set elements to be the set of I want to exclude the 0 one. So Z I for I and 1 to E. Set the residues to be a set again, a set of all the n squared for every n in the elements set that I just defined. And then I'll set the non-residues, because remember the quadratic residues are the things that are the squares of something. And then the non-residues I'll set to be the elements. Elements. So there will be a set command for getting rid of elements. Discard, I think. And we'll discard the residues. And to start getting some output that we can look at, we'll look at the number P, we'll look at the elements, we'll look at the residues and the non-residues. Can everybody see what the code is doing? So Z sets up the object, the integer, the ring of integers modulo P. So the ring it just means it's an object with the operations of addition and multiplication modulo P. We define a set. So in Sage, you can define sets like this, just like we do in pen and paper using curly brackets. We define a set of elements. Z of I kind of coerces the integer I into that object Z. So I comes from the range command 1 to P. Range command 1 to P gives you all the integers between 1 and P minus 1. Zi coerces or converts that plain old integer into an element of Z, an element of the ring of integers modulo P. The res set forms all the quadratic residues. It simply squares every n for every n in this set elements we just defined. And the non-res is the set of elements, and we discard all the residues. So it's the things that are left behind that aren't residues. So they're the non-residues. Okay. Let me simply print P elements res and non-res, so we can see P elements res and non-res. So why aren't I? Why is he printing the non-res? something. So that doesn't return the set. Sorry. Not quite right. Okay, let's just look at it this way. Yeah, it's just that discard command just gets rid of the elements, the res elements from elements. It doesn't give it back to the variable non-res. Yeah, so if I just take this, sorry about this. That in there. That's still not going to up and then do elements again. Hey, finally did it. Oh no, so discard. Discard. Okay, put those two. Let's just go like this. Okay. Okay, so what we're seeing here is the prime, the set of elements that begin with, and then after it, the quadratic residues. So sometimes we see numbers being residues. So for instance, modulo 7, 2 is a residue, but it's a non-residue modulo 11. 2 is a non-residue modulo 13. It's a residue again, modulo 17. Modulo 19, it's a non-residue, so it's not appearing in the residues. So you get different behavior there for the number 2. Other things we see there is, of course, 4 is always a quadratic residue. 4 is always appearing in the second set because 4 is always the square of 2. There's no question about it. Is it the square of something? Yeah, automatically 4 is the square of 2. Similarly, 9, when the prime gets big enough to include the congruence class of 9, as a distinct congruence class, 9 always appears because 9 is a square. 9 is congruent to 3 squared. And if we, looked at more of these cases for more primes, you'll always see all the square integers appearing in the set of residues because they are obviously quadratic residues. What's more interesting is the appearance or not of the numbers which aren't square integers. Whether they appear as quadratic residues in this under multiplication modulo P, that's more interesting. So for instance, 3 is a residue mod 11, 3 is a residue mod 13, but it is not a residue modulo 17 or 19. So there's changing behavior. And if you really upped the upper limit and looked at loads of these things, we could, so for instance, we could focus on 2 and start to try and figure out what's going on with 2. So it's a non-residue, residue, non-residue, non-residue, residue, non-residue, residue, non-residue, residue, non-residue, residue. Keep going looking for 2. Okay, 2 either appears or it's sometimes a residue, sometimes not. Okay. So does that raises the basic question of given an integer which is not a square and a prime p, can we say whether it's a residue? What kind of information do we need? Is there any kind of systematic behavior we can detect there? Now, one thing we notice just kind of looking at the rows of numbers is you can see it consistently down to that last one before they start to overflow the lines, but the residues are always exactly half as long as the elements. Okay? So that's something that's appearing as a strong, I shrink the size there to stop them overflowing the lines. You'll see the second set is always half the length of the big set. And I can't see this. You can see that's maintained pretty consistently. The second set is always half the length of the big set. Okay? So that's something we could try and prove. Okay? That should be straightforward enough to prove. Okay. So that kind of quick experimentation getting the computer just to spit out a load of examples, and you could replicate this in MATLAB as well. MATLAB has a mod command, modulo some number, the modulus. You can do all the work with that. Just build arrays of these elements and print them out and investigate them like that. But in this way, we can start to see some systematic behavior and think about starting to go improve that. So let's tackle that 50% issue. So this is theorem 8.1. So let P be an odd prime. I mean, maybe we should just declare that that's always the case, so we don't have to keep writing it. So P is an odd prime. Here's some interesting prime number. It's bigger than 2. So of the elements, of the non-zero, of the elements in the multiplicative system modulo P, which we can think of as being represented, they're the congruence classes of these integers. Remember, everything less than P is going to be co-prime to P, because P is a prime number. So all the elements less than, all the non-zero elements less than P are in this system. So of these, P minus 1 over 2 are quadratic residues. And therefore, P minus 1 over 2 are not, are non-residues. Okay, so that's what theorem 8.1 says. It's put there in the notes, but I'll just put down the main points here. It's quite you can prove it fairly easily. So first of all, I mean, so what are the quadratic residues? The quadratic residues are the things that are squares. So we'll consider the elements, and we'll just pretty directly take the first P minus 1 over 2 elements and we'll square them all. So this last one would be P minus 1 over 2 squared. Second last one would be P minus 3 over 2 all squared. So simply look at the squares of the first half of the elements. These are certainly quadratic residues. There's no question about that because they're squares. Okay? Quadratic residues are the congruence classes which are squares. Also, all the quadratic residues are listed here. What do we need to do to justify that? Well, how do we justify that? Well, certainly half of the potential ways of describing quadratic residues are listed here. Because we've got a load of squares and we've squared half of the elements from ZP. Right? The only descriptions of quadratic residues we haven't listed yet on paper are squaring the other half. Okay? Yeah.
Why don't we have P minus 2 there?
Well, P minus 2 would not be, so P minus 3 over 2 is P minus 1 over 2 minus 1. Just looking at the integer before it. P minus 2 over 2 would not be an integer. Remember, P is an odd number. If you subtract 2, it would still be odd, and divided by 2 is not an integer. So the P minus 3 over 2 is the integer before P minus 1 over 2. Yeah? So I've just split the elements here into the first half, which is 1 up to, and the last one in the first half is P minus 1 over 2. The P minus 1 element split into 2 halves. P is odd, so P minus 1 is even. So they split exactly into 2 halves. With the last one here in the first half being P minus 1 over 2. And the one before it being P minus 3 over 2. So all the quadratic residues are listed here. I mean, the only objection you might have to have to that is because if J is something which is bigger than P minus 1 over 2 and less than or equal to P minus 1, so that's in the second half of the elements, well, you see, J is congruent to P minus J. No, J is congruent to minus, I can say something like this. J is congruent to minus J, but minus J, well, and minus J is certainly in the first half. Any number in the second half can be expressed as the negative of one of the numbers in the first half. But you see, when you square both sides, you get that J squared is congruent to the square of minus J. Well, that's just congruent to minus J whole squared. Okay, squaring that initial minus sign chops it out. So J squared is already listed. It's already listed above here. We've already listed its congruence class. When I say J squared, I mean the congruence class of J squared. J squared is an element of ZP. So that looks awfully close to having proved the theorem. Here are P minus 1 over 2 elements. They are certainly all residues because they're all squares. We haven't omitted any residues because if you tried to form another residue by squaring one of the elements which isn't listed here, well, any element which isn't listed here is equal to the negative of one of the ones inside the square. So because it's negative, that when you square it, you get the same thing. So J squared is congruent to the square of minus J, and minus J is going to be one of these elements here underneath the square now. So this list does not miss out any quadratic residues. But there's still one thing to prove, because the theorem says that there are P minus 1 over 2 residues. And it certainly looks like that here, because when you count them, it's 1, 2, 3, as far as P minus 1 over 2. So I've written down P minus 1 over 2 things on the page. What we still have to worry about is, could any of these actually be duplicates? Could any of these congruence classes, are we sure all these congruence classes are distinct? So that's still a crucial thing that we have to prove. Could it be that 3 squared is equal to this one, the square of P minus 3 over 2? Could 2 of these elements here actually be the same congruence class? Because if they were, then that would mean that they were less than P minus 1 over 2 quadratic residues. So finally, we need to be sure all the congruence classes above, meaning these ones, are distinct. There's actually 2 ways we might prove this. We can actually rely on a previous result about polynomials. A quadratic residue, W, is a solution if W is a quadratic residue, this means there are solutions to x squared congruent to W modulo P. In the definition we wrote down at the beginning of this lecture, that would be the U. U would be one of the solutions. Lagrange's theorem from the previous chapter
Lagrange's or Legendre? My L.
Yeah, Lagrange. Lagrange's theorem from chapter 7 says such polynomials, I mean, that's quite a simple polynomial, x squared congruent to w. Such polys have at most two solutions.
Have at most two solutions.
That's because it's a polynomial modulo prime. And Lagrange's theorem says that the degree on the polynomial is an upper bound of the number of solutions. Because when w is a non-residue, then that polynomial doesn't have a solution. There are no x's, so when you square them, you get w, if w is a non-residue. This has at most solutions. So for one of the residues on our list above, say, let's call it j squared, we have the two solutions. J and minus j to x squared congruent to j squared mod p. So we already have, for each of the quadratic residues that I've listed here, we've already established that all the quadratic residues are to be found here. But if I pick any one of those out, pick a j squared out of here. These are all the square of something, so call one of them j squared. So it's a quadratic residue, but we can already point to two solutions to it, j and minus j, for this polynomial. And Lagrange's theorem tells us that there are no more. Okay? So by Lagrange's theorem, there are no more solutions. So we cannot have j squared being congruent to k squared mod p for a j and a k both in this range and with j not equal to k. Because j and minus j are two solutions to this. Lagrange's theorem tells us there are at most two solutions to it. So there's no more space, there's no more possibility to have another solution like a k also coming from that range 1 to p minus 1 over 2. So that shows that all those quadratic residues that I listed at the beginning of the proof are all distinct. So the residues in the list are distinct. And the list has p minus 1 over 2 entries. P minus 1 over 2 residues. And therefore p minus 1 over 2 non-residues as well. Okay. In the notes, there's a different proof given, a more direct proof that doesn't rely on Lagrange's theorem. It just goes back to the definition of congruence and divisibility, etc. So see notes for a more direct proof of this. Just before coming to the lecture, I was looking over it, but I realized we could make use of Lagrange's theorem like this, so I thought that's good to do. It's good to make use of your results. They're efficient. But it's also good to see that, you know, we don't need the full power of Lagrange's theorem here to prove this. You can also prove it more directly. I mean, just a very quick run through what that proof is. So kind of proof by contradiction, or, well, no, suppose j squared was congruent to k squared mod p for two numbers j and k from this range. Now what we're proving here is that you can't really ever have j squared congruent to k squared for j and k from this range. Okay. Well, by definition of congruence, that means p divides the difference. P divides the difference. Anytime you see a difference of squares and you're talking about divisibility, what do you automatically think about? Or if there's a question or an issue about the divisibility of the difference of squares, factorization of the difference of squares, well, we automatically remember that the difference of squares can always be factorized as sum times the difference. J plus k by j minus k. P isn't any old number, P is a prime number. Quintessential property of prime numbers is that if they divide a product, they divide one of the numbers. Euclid's lemma, we call that, didn't we? Okay, prime numbers divide a product, they must divide one of the factors. It isn't always true for composite numbers. But now look at where j and k are. But what can we say about the sum j plus k? J plus k is certainly strictly bigger than 0 as an integer. How big can it be? What's the biggest j plus k can be? Given where they come from. How big can j plus k be? Well, you just make j and k as big as possible. That, at the extreme end, that would be if they were both p minus 1 over 2. When you add them together, you get p minus 1. Can the prime number p divide any of the integers in this range? No. There are no multiples of p there. 0 is excluded. P does divide 0, everything divides 0. But then these are all numbers, all the numbers in this range are all strictly smaller than p. So p can't divide any. So p cannot divide j plus k. And what about j minus k? Where is that? Well, the smallest j minus k can be is if we happen to choose j and k the same. So that in that case, their difference will be 0. What's the biggest their difference can be? Biggest their difference can be, well, j and k comes from here, so the biggest their difference can be is when one of them is at one end and the other one is at the other end. So when k is equal to 1, and, well, I better talk about absolute value here because we don't know which one is the bigger one. So what's the largest? And so that's, well, I mean, it's certainly strictly less than p minus 1 over 2. It's actually going to be less than p minus 3 over 2. Furthest they can be apart, yeah. 1, 5, distance apart 4. Can p divide j minus k? So, well, it must divide j minus k in this argument because Euclid's lemma says it divides one of them. We've already excluded it dividing j plus k. So p must divide j minus k. But look, the only multiple of p that we can see in this interval is 0. Yeah, because these are all numbers smaller than p. But they include 0, happily this time, because they need to, because p has to divide this difference. So that implies j minus k is equal to 0. Because we know that p must divide j minus k, the only multiple of j minus k here is 0. So in other words, i.e. j is equal to k. So the only reason that j squared was congruent to k squared was we simply just named, we just picked exactly the same congruence class. So it can never happen that when you take two different congruence classes. So when you take two different representatives from this first half of the congruence class, J and K, it can never be the case that when J and K are different, that J squared is congruent to K squared. That's ruled out now. The first version of the proof relied on Lagrange's theorem, a bit of a heavy machinery to apply to it, but it does give you the result. More direct, using more basic definitions and concepts. The second argument is given there. So that's good. We've established our first definite fact about quadratic residues, about the whole system of quadratic residues, modulo different primes. They're always half of the elements of residues, half are not. So that's nice and pleasing, nice pleasing structure. Okay. The system modulo P divides into two, residues and non-residues. Something else that's apparent from the examples, not immediately apparent, but you start to notice it. And remember, in the reals, that's the end of that proof there. Recall in the reals, the positives have square roots, the negatives don't. Okay. Two key facts about squaring we understand from the real numbers. It's the positive numbers that have square roots, the negative numbers don't have real square roots. Now we're in ZP, and we've discovered that in any system, multiplicative system modulo P, half of the elements have square roots, half the elements don't. So that really suggests some kind of connection. Can we think of the residues as being some kind of positive elements and the non-residues as negative? Would that be a useful way of thinking? Would that be a useful connection to draw? The residues are the ones that have square roots, the non-residues don't. Well, actually, yeah. So we can check in the examples. You start to see how the residues and non-residues behave, how they behave. Now, what do I mean by behave? How they behave in relation to the operation. You're all extremely familiar with the classification of how positive and negative numbers behave under multiplication. Multiply positive by positive, you get positive. Multiply positive by negative, you get negative. Multiply negative by negative, you get positive. Okay, so that's a structural behavior. Positive by positive gives positive. Negative by negative gives positive. One of each, positive by negative, gives a negative. That would suggest a similar behavior with the residues. And we actually do detect it in the examples. If you look at the examples, you'll see the following rules are always followed. So we can check in the example the following rules, that residue multiplied by a residue equals a residue, gives a residue. A non-residue multiplied by a non-residue gives a residue. And finally, a residue times a non-residue gives a non-residue. Okay, we can observe it in the examples if we look, but we can only ever check a finite number of examples. So it's a conjecture, right? Some kind of thing that seems reasonable to believe it might be true. Reasonable for two reasons, because it checks out in the examples. If you try multiplying those numbers in the various examples we showed up from Sage there, you'll find that these rules are always observed, are always obeyed. And it also comes from a more theoretical consideration that, positives have square roots, negative numbers don't. Well, we've identified the things having square roots here as being the residues. the non-residues don't. So we've just formed a connection between those two concepts. It's not a proof, but it's a suggestion. It seems like there might be that similarity there. These are indeed true. Okay, I don't present that idea straight away in the notes here, but I think it's a useful thing to. I mean, it is there later on as a result in the notes, but I think it's quite nice to prove it at this stage. So let's try and prove some of these. I'll certainly prove the first one in the time available. Let's just try and prove it. Some of these are easy to prove. I mean, they just fall out of the definitions. Well, they basically all fall out of the definitions, but one of them needs a kind of a counting argument. So we'll let U and V be residues. Modulo P. These are not prime. It goes without saying in this chapter. Okay. And we want to consider the product U times V. Right? And we want to ask ourselves, is that product a residue or not? Well, to prove it's a residue, we got to exhibit a square root of it. Okay. So where's that going to come from? Well, you see, we've made an assumption. We've assumed that U and V are residues, so we should certainly name their square roots or bring their square roots. Suppose we can say U is congruent to the square of alpha and V is congruent to the square of beta. Surely the square root of U times V is going to involve somehow our alpha and beta. Well, yeah, because U times V then is congruent to alpha squared times beta squared. And what's that congruent to? All of these mod P, of course. What do I want to write as here? Yeah, square of alpha beta. Yeah. Yeah, because that proves it's a residue. Here's something that when you square it, you get U times V. Yeah. Simply, just like in real numbers, what's the square root of a product? It is the product of the square roots. So that's effectively just what we're arguing there. So that proves the first one. So one is true. Let's prove the second one. No, let's prove the third. Now we're going to let U be a residue and V a non-residue. And we'll do it by proof by contradiction. Let's pretend for the moment, assume further that U times V, and we're going to do a proof by contradiction, so we're going to assume it's a residue. If we know or we suspect it's got to be a non-residue, but we'll assume further that it's going to be a residue. So and again, we got to pass to the square root. So U is congruent to alpha squared, and U times V is congruent to gamma squared. That's what we're assuming. We're assuming U is a square, quadratic residue, square of alpha, and U times V. But you see, we can write V as U inverse times UV. Congruent to mod P. Well, what's U inverse? It's the inverse of alpha squared. And U times V, we've already said, is the gamma squared. But what is the inverse of a square? The inverse of a square is exactly the square of the inverse. And just as before, the product of two squares is the square of the product. All of those mod P. So we somehow seem to prove now that V is a quadratic residue. V is the square of something. But it can't be, because we assumed it was a non-residue. Okay. So if you ever multiply two things, one of which you know is a residue, and if it turns out the product is a residue, that implies the other thing has to be a residue as well. So that means, so U times V, under these assumptions here, U be a residue, V a non-residue, so U times V is a non-residue. So 3 is true. And an exercise for tomorrow, prove 2 from these. 2 is the only one we haven't proved. And a hint is to use theorem 8.1. Use the theorem we just proved that half of the elements are residues, half of them aren't. Okay. Okay, it's 10 to 10. So I'll see you again tomorrow afternoon, evening.